Okay, questions? So, Zach sent me a mail saying, wanted to know what it means to be successful in this course. So, it's only fair that I. Lights. Do I have a way to control this from here? Better? Okay. So let's talk about what it would mean to be successful. Okay, so you've got 60% of your score for projects, 40% for exams. You want to do well in both. So to do well in projects, you should do what? Start early. Start early, right? So and of course, use Piazza. I'm glad Zach's been using it, and really you should use it to ask each other questions. Some of these things are API details. I mean, it's not as if I know any better. Okay. And to do well in exams, what should you do? Study the material, and what else could you do? So, what kind of questions I'm going to ask you in exams? In general, I have three kinds of questions. One is, if you've been even half asleep in class, you should be able to answer those questions. So you'll think they insult your intelligence, but it's important to get some confidence points right there to get going. It's like when you're playing tennis, you want to warm up in the beginning, just to know that your serves are going in. And some of these will be questions I ask in class, and maybe two people answer, and the rest are thinking about the answer. So that the two guys who answered are going to be able to get that question. Okay, but the rest you need to study. Okay, so basically things that are subtle. Hopefully, we are talking about things here that are not that obvious. Okay, so there are some obvious things, and those will be asked. There'll be some subtle things. Subtle things, by definition, require some thought or some studying to sort of get that stuff in. So studying will help. Okay, being in class will help to get the first question right. Second kind of questions is to basically study, and the third is get a good night's sleep. Okay, because I'll ask you some things that will build on the first. Okay, so you will get warm up, you will get to sort of answer a subtle question, and then we'll go a little bit beyond that. And I used to have three questions, each question with three parts, with A, B, and C, and the C part was sort of the ones that build on the A and B. And believe it or not, there are these smart guys who don't like to study, who would get the C part right and the A and B parts wrong. It broke my heart, and I would give them a good recommendation. But you've got to get everything right. So those are the three kinds of questions. So, everything I say is going to be in word, in audio form. If you want to take notes and write down in a more succinct form, good. But just keeping your ear open and listening and discussing would be the best way to prepare for class. Okay? That's just because that will just make everything sink in. Okay. Any other questions? Small questions, big questions, doesn't matter. It's good to discuss them. Yeah.
Small question about the homework.
Yeah.
So I was looking over the questions you asked us to consider.
Okay.
And one of them was how might you share code between the synchronized the various.
Between the various.
Yeah, and this might be a completely stupid question, but I wonder why you need to share any code at all, not just the message.
No, when you're writing. No, sharing. No, I don't mean dynamically sharing code.
Yeah.
I mean, you're going to write multiple programs, right? Maybe you're going to do peer-to-peer, in which case everything is going to be one program. If you're going to do a server and client, it'll be good to share code between the server and client, and do that after you've got the thing working. Okay.
So it's more of like architecting it.
Architecting in a modular way. If you look at the tutorial that the guy wrote, he said, look, please don't hold me, to reuse. I'm not trying to do reuse, I'm just trying to get the concepts across. So try to imagine how you might abstract out and share the code. And later I'm going to show you a way I did it.
When I read it, I thought you meant something like actually like remote method invocation or something strange as opposed to
Yeah.
I was like, how does that even fit in here?
Yeah. Well, there have been designs where you dynamically transport code from one address space to another. You can do that in Java, by the way. You can just, in fact, we will talk about things like this. that how can you actually pass a method across, a class across to another process. That's one of the nice things about Java's RMI, that it allows you to do that, though it makes it hard for you to use that feature. Okay, but so there's migrating code. I mean, I've done actually some research in that area, but that's not what happened.
Okay, yeah, right. So in essence, this is just message passing. The message being the input domain.
Right. And I'm just saying, you know, the more if you abstract out and share code, you'll understand better what you're doing. Okay. Other things? Okay. So you've got a flavor of what's happening in this course. We're looking at very nitty-gritty things, you know, implementation details, not just the high-level use programming. And you know how to use pipes. We were seeing how pipes are really implemented. And in general, you can have multiple clients and servers, if you want to call them clients and servers, multiple processes talking to each other. And the one constraint is that all of these processes must have a common parent. Okay? And so how do they know about each other? We saw that they basically they have file descriptors, and the file descriptors are bound to each other because of a parent. Okay, so we saw to make pipes work, we need some features from the operating system, and I believe these features were created just to create pipes, or basically to do I/O redirection in general. So in general, you have a standard input, standard output, standard error as 3 file descriptors. Okay? And and these are kept in a file table, which is kept in the kernel space. Okay, so this is scarce space, and you can overflow this space. So I don't know how many of you have ever seen this, but you sometimes get a message saying out of sockets. Okay, because sockets happen to be file descriptors, and your program has just created, your system has created too many sockets, so the file table is confused. Okay, so that's one piece of space that is known to the operating system and maintained by the operating system, more specifically the kernel. Okay, so the operating system versus kernel, I kind of mentioned briefly what's the difference?
The difference between
kernel and operating system? So it is some subset of the operating system, some core. And so, you know, how do we decide what is the core and what is not the core? So somehow things can run. A lot of functionality can be provided by the core without having the rest. So the rest of the stuff must depend on the core. Now, we do have things put in layers, so you can say that every layer is sort of a core for the layers above it. But somehow, at some point, you say, okay, these layers are the kernel, and these layers are the rest of the operating system. Okay. And is there some litmus test? You can look at an operating system and say, this is the kernel, and this is not the kernel.
stop executing kernel mode versus user mode?
Okay, so that is true. The code that runs in the kernel mode is kernel, and the one that does, so you can just see what happens there. That's a good way to look at it. Any other way? So how you enter a kernel mode, what makes a computer go from user mode to kernel mode? System call. Underneath there's a trap, but that trap is invoked by the system call. So basically the kernel will be the collection of system calls. And these systems call will together provide you with the abstraction of a process. Okay? And they'll typically also provide you with IPC, inter-process communication. Now you can build daemons or servers that are outside the kernel but do operating system functionality, and you invoke that functionality not by making system calls but by doing what? So this functionality will be provided by daemons. These are processes. These are operating system processes. You as a user create user processes. User processes can invoke kernel functions by making system calls. They can go and invoke the services provided by server processes by doing two processes need to talk to each other. They need what? IPC. And that is why the kernel will provide you with IPC and processes at the minimum. It may provide more. Okay, and the big issue has always been the file system. Should it be inside the kernel? Should it be outside the kernel? Inside the kernel is fast. Outside the kernel is flexible. And people have been sort of, you see people changing decisions around this, decision about this aspect frequently. Okay, so anyway, these features are provided by the kernel, as it turns out. And so one of the features is that you can do a fork, and later you can do an exec after that, and we'll see why these two things are separate. But when you do a fork followed perhaps possibly by an exec, what happens is, okay, so this is the space that is kept in kernel. This is the area that is known to the operating system, known to the kernel, maintained by the kernel. There's also space known to the kernel that is inside the process's address space, and that's the environment. Okay? And so that can be big. That's where you can create long variables, long class paths, whatever you want to. You'll never run out of these unless you overrun your stack or your whole memory space. And what happens is that when you do a fork, you get the child process gets a copy of this table, and also in the space that is allocated to it by the compiler, the environment, it gets a copy of this. Okay, but this is what we're interested in.
So the file table is part of the process control one.
Yes, yes, and it's a three-level thing there. There's a file table that goes and points to a file descriptor table, which goes and points to an inode table. Okay, so when two processes happen to share the same file, I'm reading the file and you're reading the file. Why do we need any sharing there? I'm reading the file, you're reading the file. The file is on disk. Do we need to share any in-memory data structures? No. When you get this descriptor here, that's a copy of the descriptor here. Along with the descriptor, you're doing stream I/O. So what are you maintaining with each file? If you're doing stream I/O, you must maintain position. Okay. So when you go and get a copy of this, you get a copy of data structure. Also, you are pointing to the read-write mark. So if I go and advance it, and you later read it, and you have gone and got a copy of the descriptor, you will read the next byte after that. Okay. So that is why it's a complicated structure. Okay. So you need to share the read mark table, perhaps. Also, you want to share the cached values, right? If the file has been copied, even if you're not sharing the read-write mark, you want to still share the cached contents. Okay, so that's why you need a three-level table, and that's what it is. But basically, you start off from here and you go then to a common table, two common tables that are kept for all processes. Okay. Okay. So you get a copy of these descriptors. Okay. Other questions about this? And that's the feature you have. And then to do the pipe, what you will do is you will create pipe in, pipe out. You will create a child process which will get all of these. Okay, so you have managed to inherit the read descriptor and the write descriptor. But you want these two descriptors to be standard input and standard output. So what other feature do we need now from the kernel? We need a system call to redirect, or I really want this value copied. And anybody know in Unix what that call is? It's called duplicate. Okay, so how you basically copy this value there, and then you can go and close this descriptor. So you've got a close call, you've got a dupe call, you even got an open call, but the open you didn't have to make. Okay, that was done by the parent process. So you get this. So that's how you got this value done. And so can copy file table entry to another position, can close it. Okay, questions? So now we get to see that we've got two processes. The first process goes in, opens pipe in and pipe out, and then both of these child processes get these descriptors. One of them copies pipe out, and one of them copies pipe in. Okay, and you get a picture like this. Okay, and right now all of this code is still the shell code. Your ls, your cat code and more code aren't executing so far. Okay, but you've set up the tables, and now what will you do? After fork, you will do exec. And exec says, keep all my tables, just change my code now. Okay, and like I said, that was meant really to support something like this. Okay, and if you have n processes connected in a pipe, you've got to either do it recursively or iteratively. You can do it both ways. It's a fun thing to do. It's a fun thing to do, actually. Okay. And I mentioned last time that you often wonder why are fork and exec separate, and here's the reason why. And a long time ago they did a survey to see does anybody else ever do a fork without doing an exec after that. And in that survey, they found only one program that did not follow a fork with an exec, and that code was wrong. Okay, so this is the main motivation, or maybe the only motivation for having fork and exec. Okay, and this is some stuff invented when was Unix invented? 60s, 70s, early 70s, late 60s? So still around. Yeah, it's amazing. You guys know how the word Unix came around? What does Unix mean? There was Multics before it. It's a beautiful system. Okay, when you want to teach operating systems, you take Multics. They tried everything. Okay? And when you want to teach programming languages, you take Ada. They tried everything. Both of them were very unsuccessful. Okay, so Unix was sort of saying, hey, we'll do one thing right. And I don't know what that one thing they meant was, but everything is a file is one of those one things, I think. But it was a much skinnier version, and so Unix came from Multics. Okay, Multics was in the 60s, late 60s, MIT, Bell Labs, and so forth. And I think this was also the 60s. Okay, questions about pipes? Okay, so the nice thing about pipes is to send data you write to a stream. To receive data you read from the stream. Reading and writing is something you learn in 101 programming. Okay, so inter-process communication is 101 programming. Right? Great, easy. Slight issues, So what about, if I go and write something, when does the write call return? Okay, let's talk of file I/O. When I write to a file, when does a process writes to a file? When does the write call return?
When it's done writing all the bytes to the buffer that will eventually dump it into the disk.
Okay, so we don't wait for it to be written to the disk, because this write call may be replaced by another write call that goes and changes the data, and why should we go and bother the disk? Okay, and so when it's done, and so by the if it's written to the system buffer, it's done. It will get there, unless. Okay. So if the power cord is pulled, there was this joke. This DEC guys had this joke that the IBM computers would save one piece of information, and the DEC computers, which was when IBM was powerful, the upstart was DEC, which is now compact, I guess. And so when the power when the power goes down, you get a power interrupt. Actually, the operating system can figure out the power is going down. So the IBM guys would say, the DEC guys would save your system buffers. Your work, the great piece of this great sentence you wrote. It's saved. And the IBM computers would save. This was in the time sharing system. When things were charged, they would save the accounting information. How much do we charge this guy? Okay. So the joke went. I don't know whether that was true or not. So, okay. So when should this send call when you have a pipe, and the writing process should block until, based on what we know about file I/O, it should block until.
It gets written to the buffer, but then you get into this problem where what happens if the other process doesn't finish receiving it?
Oh, the other process is slow, and this process is fast. Okay, and you might run out of system buffers. In which case, what should you do?
Stop writing, which finishes up. But then you have to block the write until the buffer gets empty.
So you have to block the write. Interesting idea. So there is one process that's producing data, the one process that is consuming data. When the process consuming data finds nothing in the system buffer, it will do what?
This has happened to me. If you do tail and grep, and you're trying to continuously filter the stuff that comes through, I forgot what you have to do.
You have to keep feeding it something, right?
Yeah, but what happens is like tail, it'll like put stuff out and it will be buffered, and so it doesn't go through grep, so it just looks like nothing's happening.
So just think of first principles. You have this buffer. One process is creating data, you would call that process what? You have one process that's reading data, you would call it a, and you would call this buffer a, what did you just say? When the buffer is full, what should we do?
So we should block the write.
And so that is exactly what happens to a producer when the buffer is full. And when the buffer is empty, we have a bounded buffer. We have an application of a bounded buffer. All that stuff you guys learned in operating systems was relevant, believe it or not. Okay, there's a bounded buffer right here. Okay, and we'll get to your issue soon. That's even more fun. Okay, sender waits for non-full buffer. Receiver waits for non-empty buffer. And trust me, guys, you'll be using bounded buffers galore. Okay, you will really appreciate what you learned. Okay, and allows lazy evaluation. Okay, I'm going from operating system to programming languages. Lazy evaluation. What does that mean? Anybody know?
Just took it last semester.
You weren't taught well, or you were not a good student. One of those two things. How can you forget this one?
I'm lazy.
That's the whole point. When I learned this concept, I said, that's me. That's great. So should you do your assignment, I told you, to be successful in class, start immediately. That will be eager. Or wait till the last day. Now, sorry? So basically, lazy means, just delay as much as possible. Because I might just go and change the semantics of the assignment, and the poor guys who started the first day, I had to implement that, and the last guy said, I get the latest version. Okay? Who knows what might happen if you don't, so just basically evaluate when on demand, near the deadline, rather than early. And most of us are deadline driven. Okay? So do something only when it's necessary. Now, can you see how that's relevant to pipes? If I'm the producer and I'm fast, and there's a consumer that's very slow, which might even die. Okay, we have doing cat to ls, and somebody can go and just kill ls. What would be the harm of doing eager evaluation? Who's doing the evaluation? There's the producer and the consumer. Okay, let's think of the producer. Can the producer do unnecessary computation?
If he keeps trying to write to the buffer, assume that it has some semantics. If the buffer is full, I'll just add some more information to it. I'll just replace it with the latest version. If it doesn't know that ls has failed, it will just constantly write to that buffer unboundedly.
Yes, and there's no one to consume.
Right.
So what is the point? It's like a tree that fell and nobody saw it falling, right? It never fell. So it's one of those things. Okay. So do not do computation that's not needed. That's basically the point. Okay. So what if you have this semantics? Okay. You have this program that just produces something in infinite loop. And you say head minus 2. Anybody know the head command? Top n lines. Okay. This guy just wants 2 lines. This guy wants to produce an infinite number of lines. We don't want this guy to produce more than 2 or more than the bounded buffer number of lines. Okay. So when this process dies, okay, we want to send some kind of, we want to kill this particular process also, because there's nothing to consume. So what's the point of keeping him on? There's no output. Okay, and assuming that all semantics is output. I mean, if you have no more output, there's nothing to do, then this is true. Okay, and by the way, talking of lazy evaluation, there was once this compiler contest. How fast are the various compilers? And the one that won was one that did lazy evaluation. It looked through the code and saw there was no output. It just didn't even compile it. So that's an example of lazy evaluation. Okay, so infinite output producer blocks after filling buffer, and head grabs first 2 lines from buffer, closes pipe, and terminates. And parent shell, waiting for the head, unblocks, basically unblocks and kills infinite output producer. Okay, and what if my producer stops before I have finished what if the producer dies before the consumer? You're done, and you will get in the consumer error. an end of file. You just say, okay, there's nothing more to read. Whatever you do on end of file, do. Okay. So this is an interesting IPC semantics that we don't see in modern IPC systems, but it's a pretty good concept. Okay, so pipes historically were built directly in the kernel at one time, and then 4.2 Unix BSD. What does that stand for? Anybody know?
Berkeley software distribution.
Yeah, so the Berkeley software distribution. They created sockets, which we'll see next, and then pipes were implemented on top of sockets. Same semantics. Okay. Questions? So pipes, great redirection to different processes. This I/O redirection is just a wonderful idea. But the problem was that processes on the same computer with common ancestors. How many of you guys use pipes? You use pipes. You do some command line programming. But the ordinary person no longer uses pipes because the ordinary person uses GUIs. And what does it mean to do I/O redirection in GUIs? That's a real challenge.
It's copy paste.
Hmm?
Because it's copy paste when you have a GUI.
Yeah, it's copy paste. But these mashups, I feel, are somewhat in that spirit. That basic idea of pipes was composition. You could just build new commands from old commands. And these mashups also are sort of like that. That you had write isolated program here, isolated web service here, interactive, and they just combine together into one composition. So that's how I am understanding that. Okay, so it's a good idea to connect processes together. It's just that this teletype I/O is now boring to people and copy paste or whatever.
Windows PowerShell was pretty new, and they put pipes in it.
Yeah, sure. If you're using shell, you need pipes.
Yeah.
For sure. Windows PowerShell, is that like an oxymoron? I'll tell you. So Bill Gates is a smart guy, right? But he never went to college.
Well, he went, he just dropped out.
Well, so he didn't finish his degree. And being an educationist, I have to, of course, look down at that, right? Even though he's a very smart guy, apparently. And he hired a lot of people who didn't go to college, who were very smart. And the reason I've heard, and I've spent some time in Microsoft, I've had their soda, okay, so I'm somewhat loyal to them. Apparently, the reason why their shell was so bad was that those guys who created their Windows shell never learned parsing. Okay, if you do the Unix shell, they use Yak there. It's done. These guys just did repeated scanning to do the command line. So they were limited by what they could do. They were very smart guys, but they were lacked in education. And so that's why their shell was just so behind. So that's why they need now a PowerShell, I guess. But anything PowerShell has that Unix shell doesn't?
I think the most interesting thing is Unix passes text.
Oh, this one does GUIs?
No, the PowerShell passes full objects. So if you have a .NET object that's like person, in the shell you can do like person.firstname or have birthday or any kind of method. So it passes full objects. So you don't have to parse the text.
But you're reading objects from a stream?
I mean, when you're doing the pipes, I'm
Yeah.
not sure exactly what's underneath, but like.
But that the pipes, is that how it is? You stream a bunch of objects to another process?
Yeah, so it's like everything is a collection of objects.
Okay. Stream of
From
objects.
the pipes,
So
yeah.
you guys actually can do that. I mean, you guys will be doing serialization. So you could implement that feature, actually. Good. But the thing is now it's all event-based thing, that you don't have a stream, you have event-based. And because of event-based, it's hard to do something like a pipe. Okay? The X window system is somewhat like that you can redirect the I/O to one process or another process, even though that's GUI based. So you can imagine that being in that spirit, but otherwise.
Yeah, kind of the functional reactive programming stuff. It's a stream of events, and so they kind of have that, passing it and like having functions that like modify the stream so that the final output of the stream is a function of the input of the stream.
Okay, so you
It's
can put some filters in there.
Yes, it's like if your mouse is moving, you can filter like the X position.
Mm-hmm.
You can do like the sign of the X position.
Right.
As you move your mouse.
Yeah. And this whole idea of remote desktop, etc., is some form of I/O redirection, actually. In that. Okay. So, the problem is with pipes is that these processes that are talking to each other must be all have a common ancestor. Okay? So now we want to go beyond that and allow processes, and these were introduced in Berkeley. And again, this has stood the test of time, right? They were done in the mid-'80s or early '80s, and we still see sockets in some form or the other. So it either means that they're so good or, we as a community lack imagination. Okay, one of these two things. But they're there. Okay, and it's amazing, again, having spent time in Microsoft, it's, you often wonder whether the researchers are doing anything useful because, after all, the products that you're using are created by the product guys. And the product guys, it's very hard to make them move. I mean, there's MSR there doing wonderful things. And who copies them? Google does. Not the Microsoft guys, really. I really know specific ideas that were copied by Google from MSR other than Microsoft. Because they just say, if it ain't broke, if nobody's asking and clamoring or something, just keep doing what you were doing. Okay? So things don't change that much. Okay, so what do you guys think of sockets? So how many of you have not used sockets? Raise your hands. Okay, one person. Two people.
Like directly or in any form at all?
Well, when you run a web browser, it's using sockets underneath. No, directly. How many of you have not programmed using sockets? Okay. Those of you who've programmed sockets, what do you think about it? Are they? Huh?
They're pretty awesome.
Awesome?
It abstracts out a lot of the network headache. It's nice.
Anybody think they're not awesome? So if I was to ask you to program, do you have the conceptual model in your head, or do you have to look at a tutorial?
I've done it fairly recently, but on the spot, probably not.
So you can always take some working code and morph it to make your code work. But can you write that code from scratch? Okay, like you can write a for loop from scratch.
I mean, probably get hello world gets it across the network connection.
You think you can? Okay.
I don't.
Oh, good. That's good. That's pretty good.
Hold on.
So sockets are, they're pretty general. And because of generality, they're somewhat, we'll see how much you know of sockets when we just covered it now. And it's, there are books on how to do socket programming. There's a guy called Stevenson? He's written a book on how to use sockets. You should not write a book on how to use sockets. The abstraction should be right. You don't have a book on how to use for loops. So in my viewpoint, there's something wrong with them also. Okay. So let's go in actually, let's just go and, let's go and put ourselves in the shoes of the Berkeley guys. Okay? They wanted to be very general. They had pipes. They wanted communication between processes in different machines. Now where would you go? What would you do? What incremental steps might you do? Let's go and derive sockets. Okay, I'm going to derive sockets in a nice way, so, they won't seem as complicated. But when I've asked this question earlier, people said, oh, it's a mess. We know how to use it, but we don't know quite the model. So we've got a way to do writes and reads. Would you still keep that in sockets?
Yes.
And okay, so you would still read and write from file descriptors. So what's the challenge now from going from pipes to sockets? We're going from processes that have a common ancestor to processes that are arbitrary, maybe on separate hosts. Okay?
You can do name pipes or processes as well. So you still have the same.
Okay, so we'll have to see what named pipes are. Maybe we're going to derive named pipes here. Okay? So tell me the unnamed pipes that I gave you. Okay? How would I modify those to do or go across the network? And that brings up the naming issue. So I have a file descriptor here. I have a file descriptor here. And they have to be bound. When I write to one, there should be reads in the other one.
You need an address in the other one, which would be a full.
So let's back off. Let's not go and commit prematurely. We need an external name. A name that is outside the address space of one process. Okay? That's what OSs do. OSs name things that are outside processes. Programming languages name things that are inside processes. Okay? And what's the standard way in Unix to name things outside processes? File names. Okay? So we could have file names, or we could have what you were talking about. Okay? So that's one issue. So we have some way of sort of, one process will advertise a name and another process can use that name. Okay? That way we have, just as when I write a file, one process chooses the name for the file it writes, and then another process uses that same name. Somehow I learned about that name. Maybe, how do two processes learn about names, by the way? How could I learn the name of one of these named pipes, as you put it? Publish it, just call up the guy and say, this is the name. Or publish it, meaning put it in documentation, or even more dynamic, have a special server perhaps that's responsible for names.
Oh, a dynamic name server.
You would call a name server. You have a name server perhaps. Who knows? But we need an external name. Okay? So that's one thing. Let's go and see how the slides are going. So we need to connect the descriptors. So we need external names. And, depending on who's, either party could name. Okay? We got to figure out that. But somehow one party has to name and the other party has to use the name. Okay? So somehow, sorry, that should be one word. Messages sent to socket in one process must be received by socket in another process. Okay, we are going to call these special descriptors then as socket descriptors. There'll also be 5 descriptors, but there'll be socket descriptors. Okay? We will write to this descriptor, somebody will read from this descriptor. And somehow the message sent here must be received here. And how would that happen? We know that one of them has a name that is known to the other party. Let's assume that this guy has created the name. Okay? So the sender has to send a message here that gets directed here. So what other things have to happen to make sure that my messages go to the right? How does sort of, yeah?
You have to have some network protocol between them.
Some kind of
network protocol.
So what exactly would happen there? What would happen there? I mean, you can always go and send messages across, okay? But we need some way to go and say it should go to this guy's descriptor rather than that guy's descriptor.
Each packet needs to have a header of the descriptor.
And that is underneath what the network's doing. Is that something you want to expose to the programmer also as an operating system? Maybe. No, don't give up.
You need a port number. You can't just say to go to another machine. You have to be able to speak specifically to an instance of running application.
So let's not commit to port number, file name. We have an external name.
Yeah.
We have a way to say, we have a way to name this socket somehow. Okay? And it may be a file name. It may be a port number and a host number together. Okay? The file name makes sense when you have a network file system. Okay? Because then these guys all share one network file system. So you can use that name, or you can use the host and port number. So now, as I am writing data, do I go and write with each write? Do I go and say to this external name? That's what the network is doing, right? The network underneath is saying with each packet goes the address. But when we're working at the OS level, do we want to go and say with each write the external name? Then our write will change because our write doesn't take any, the current write, the file write doesn't take any argument saying destination. It just writes to a stream. But that is a possibility. We can go and change the write to a send and say send data external name. And do you think sockets allow that? You experts on sockets?
Problem buffer too.
Okay, buffering is yet another issue we'll worry about. We'll go one step at a time. So, those of you who know networking, TCP/IP, and what's the dual of TCP/IP? And TCP/IP is, the difference between the two of them is? So one is stream-based, one is datagram. Do you think at the OS level you should have the control over whether it should be datagram or stream? When network guys are providing it, you don't want to, not expose it. So at the socket level, maybe you should allow this. Sorry? So then sockets do allow that. And because they allow both, it becomes hard to master that because they try to do everything. It's not as if there's one UDP and one TCP. We have sockets that can be UDP-like or TCP-like. And that causes a lot of confusion. Okay? So we need external names. External name could be, and this is what it can be, yeah.
Do Windows sockets allow for write and read, or is that just Linux?
Probably. I don't see why they shouldn't.
Well, they're not file descriptors, I don't believe. They're like some, just like a socket structure.
So that's just a layer above, I think. Underneath, it is going to be sockets. Okay. Even in Java, you don't have a descriptor, you have a structure. Okay, but underneath it's descriptors. Okay. So by the way, the naming scheme, when sockets came by, they had multiple naming schemes that made them complicated. There was the INET address scheme, which was the internet scheme, host and port number. And there was also the AF Unix address family scheme, which was just in Unix. This is not in Java, where you just use file name. I should make sure my... So this doesn't exist in Java, apparently, from what I've said here. Okay, but that was, when I first used sockets, I used this particular thing. Okay, I said, oh, wow, this is so cool. And I used the file name as the external name. Okay? And somehow messages to, and there is something called a datagram socket in Java. Okay? In Unix, it's all sockets, but you basically say, I've got a datagram socket. I've got a datagram socket. They're both subclasses of some form of socket. And I create a packet, like you were saying, where I go and say, this is what I want to send. And so this is my receive. I'm sorry. My receive just goes and says, I want to receive this buffer. And my send should do what? It should also take, I've got a missing comma here, buffer offset how much, what I want to send, and where I want to send that stuff. Okay? And so it's got the host and port number also. Okay? Could multiple processes share? Yeah. Underneath in the operating system, yes, they do. They're file descriptors. Okay? In Java, when one process creates another process, I don't know what the semantics are. And I think you don't really fork processes in Java. You just exec them, and I don't think there's any sharing of space there. So I think Java will hide that away from you. But I may be wrong. But underneath in the operating system is happening. Okay? I don't know how exactly Java has camouflaged that or hidden that. Okay? Okay. So, clear? Datagram socket. Did you guys know what datagram sockets? Okay, something new you learned. And you can see how we're building incrementally. Okay, so what's really going on is that you can have a receiver listening on one datagram socket, and senders sending on, actually each sender will have its own datagram socket. I'm sorry, this picture is not very good. Okay? So each sender will have its own datagram socket, which is going to this datagram socket, right, like this. I should modify this picture. Okay? So they're not, they're logically one datagram socket, but they're physically different datagram sockets. Okay? And this guy is receiving, and this guy is sending. Okay? Can you have it the other way around also? That on the sender is sending to one datagram, using one datagram socket to send to multiple machines? Certainly this guy is receiving packets from multiple machines. Each sender goes and says, this machine. Can you have the other way around? Same thing, right? Because I can use the same datagram socket and send packets addressed to different places. Okay, again, this picture is not good. But you have separate datagram sockets for each process, but they're all connected to one datagram socket. Okay? So now, again, you have the sender here and the receiver there. But that's the generality. It's like pipes can be used by n processes at the same time. But typically, there's one producer, one consumer. It's not really multiple producers and consumers. So typically, you'll be using a datagram socket to talk to the same receiver again and again. Right? So can I just as an API designer make things a little bit more convenient for the programmer? When you're if your datagram socket is going to, if your message is going to go to one particular receiver, can I make your API a little easier?
Specify the port every time. You don't need to specify the location every time.
At every time you send,
Right.
which must mean that you must specify it at some earlier time. Open, or in our case, we do a new socket, datagram socket. And then what kind of API could we use to write? If we have somehow told the system what the destination is, what API would you use then? File API, we can go back to it. The good old familiar file API. Everything is a file, including now a socket. Okay? So, what we do is we do a new, that's what we were doing so far. And what we'll do is, rather than doing a new datagram socket, we'll make a separate kind of call here. We'll still have underneath datagrams. But we're just going to have a separate API now. And we're going to just say new socket. Okay, we're not going to say datagram socket. And anybody, any idea what this false means?
Blocking.
Or it is not blocking. Blocking happens in non-datagram socket. So this means it's not. It is datagram.
Oh, okay.
It's not datagram. It's not stream. Okay, because stream is the one you will go for. Okay, you want reliability typically. Datagram is the exception. The rule is stream. Okay, so I have in my socket call. Okay, yeah, both sockets calls say, whenever I do a send, who the message should go to. Okay, and now I can just go and say socket.get input stream. Okay, and I can read and write from this stream. Good old calls. Okay, so we are just saying, okay, the most general case in Datagram is that, the previous one, and now we're going to this case. Okay, so this is a call that, this is the kind of stuff that you use, but you haven't quite used this either. Okay? When you when you write your hello world program, you send hello world from one process to the other. Is this what you did, or you did something different? See how difficult it is? I give you an example and it says, is this correct or not? And that's hard. Then coming up with your own example is even harder. So I kind of prove my point that sockets are not the most intuitive abstraction. And if they're not intuitive, it's because they're very general. It's not that those guys were wrong. Okay? Because I'm deriving this very incrementally in a very systematic way. And you can't argue against the way I'm deriving it. Okay, so you guys do not use datagrams. I think for all I know, the datagrams may be deprecated by now by Java. I don't know. They did exist at one time. So when you want to do TCP/IP, how would things change? I've actually brought things closer to TCP/IP by going in this way. So TCP/IP is reliable, and it is stream-based. I've kind of gone to stream-based, but not reliable. Right? So to make it reliable, I would need to say what? I would need to make this true. Okay. Anything else I need? Would it be so symmetric? This is very symmetric. Both processes go and specify the other processes host and port.
Would you specify a listening port one?
Yeah, you have to have a listening port for the server socket.
So what's really going on there? This is, what we have is the system doesn't know about this. There's a stream. There's just some sugarcoating in the language that has got the stream. The underlying network operating system doesn't know there's a stream. So you want to create a stream, right? And you want to be able to create the stream as an individual entity. So you have to have a named stream, if you will, or a named pipe, or whatever you want to call that. Okay? And so, what's a server socket? What's a server?
So it's where the initial connection is made, and then essentially a new socket is created for that particular connection. It's just like handed off. That's like sort of I've heard it called like the door knocking. I don't know. I heard some analogy about like It's the door you knock at, and then given an individual socket. So it's the known port that you can go to.
So, let's forget about the reliability. One thing we don't have is a private channel. There is no way for one process and another process to establish a private stream. Forget about reliability. Reliability is sort of another issue. Right now, we've got every port. On one Datagram socket, you could be receiving messages from anybody who can address you. Okay, so we need some way of private channel, and the question is, it seems like an oxymoron again, right? I mean, we want a private channel between a client and a server, but that can't happen if there's no public name. So what do we do then? You negotiate, but for negotiation, the starting point is going to be some public name. So we have this server socket, which is like the door, perhaps. I don't know. I don't quite, I'm not gelling with this door analogy.
That's not a good analogy.
But I don't think there's a good analogy, and that's why part of the reason why sockets are so confusing. Because I think they should have had two different. They should have had a server socket, client socket, and socket. That would make things clear in my head. Okay, but they have the socket thing that is sometimes talking to a server socket and sometimes talking to a socket, and this overloading, I think, confuses issues. Okay, so if I was to redesign it, this is what I would change. So by the way, why do we need private channels?
Possible for someone else to connect and then they need your data.
So, in this world of, and so if I want to start a session of some kind, okay, and remember these IPC mechanisms were all invented for this one application, a file server, and they always said a file should be represented, a distributed file should be represented by a socket, and so that file is something that you opened. And you've got an offset within it, which you don't want to share with arbitrary other processes. So we wanted that kind of private channel. Okay? And from Datagram to Stream Socket, we're going to have private channels. So you're going to create a public name that's going to be used to create copies of private channels. Not shareable channels, but this is sort of, if I've got the classic example is that there's a file that different clients want to open. With that file, I will create a server socket. Everybody who wants to open that file will get a separate private channel to go and read the data at their pace, using their offset. Okay? So we have the server socket, and now server socket just takes port, no host. Okay? Because this is going to be, the other guy is responsible for somehow connecting to it. So we now have a connection ID also. We didn't have connection earlier. Okay, we just send messages to each other. Now we're going to have a connect. Some guy's going to advertise the name. Some guy's going to use the name. The guy who's advertising says, hey, operating system, you know what my host is. Okay, here's the port within that host. Okay, that's my server socket. And I guess you can do the, I'm not sure why I'm passing the port number again. You could do this without the port, and then you would have to do a bind call, saying this is my external name. But at this point, I am doing what? So the bind call in sockets is what?
It's when you're asking the OS for permission to listen on that port.
So this is the listen call, right?
Yeah.
So you block at this point?
Yeah, you wait till you have a connection.
No, that's the accept call. See, even I'm confused.
Oh God. Maybe I can't read the world.
So I think I've got a little mistake here. You can just do server socket and bind later, or you can just do binding at creation time. I think that's what I'll assume is the truth.
So like if you give it a port during the constructor, it goes and calls bind.
That's what I was going to assume. But I know in Unix, you did create the socket and you bound it. Okay, that I know. In Java, I'm just kind of, I never use sockets in Java actually. Okay, I kind of did for your assignment. Otherwise, I just use RMI, which is higher level. So this guy is going to do a connect. He's going to say, please, my socket should be associated with this socket. Okay? So he's going to give the host and port address. And now what's going to happen after this?
That returns the socket to the client.
Yes, that's already got he's already got a socket. He's already got a socket. He's just going and making a blocking call.
Yes. And then that opens up the input and output streams for that. So you can have that.
No, but okay. So after the connect returns, you can start using the socket to write and read. What about here? What happens at this end?
You have to have an accept call.
Which will do what?
It blocks until the connection's established and then returns a socket that has its own input-output streams that mirror the ones on the client.
Okay. So this is where you're going to do a server socket and you get back a socket. And that's your private channel. So after the connect call, I'm going to use this socket to read and write and talk to this guy. But before the connect call, my socket is going and talking to this guy, which is what I find confusing. And I would just have a client socket. You go and connect to that socket and both of them will return sockets to you. That would be a little bit more intuitive. Okay. So at this point, you have this picture where you can say socket.getOutputStream, you can say, and then you can say outputStream.write, or you can do reads also. Okay? So we are using still the same I/O underneath, but before we could do the I/O, we went through this protocol essentially. Okay? Where we bound the port and we listened for connections. In the Unix call, you could go and listen for and say, I would only accept 10 or 20 connections. Yeah, but it seems that they've hidden that away from them. Or they might have it. Okay? Questions? So again, my picture is not the most perfect picture because it shows one socket here. But you see these blue lines and red lines, and what do you think they mean? You know, we tend to draw lines for everything. So the blue lines are the bind, accept, the connect call, and the accept call. And the red lines are the message passing lines. And because there's the same socket, there's two kinds of traffic passing through this, is the issue. Okay? So each client can, and now of course, you know, if this particular process that's going to connect, if it's in Unix at least, if it forks other processes, they can all write to that socket. Okay, but if you're not forking processes, it's only that process that you write. Okay. So this is just saying that, okay, now I can have a particular connection representing a file or some dedicated connections, a session. With Bank of America, I've got a session, you know, that's my private channel. I don't want other people snooping on it. Okay. So this is just to get a private channel. Now we can add to the private channel the idea of reliability and in order. And it so happens that the underlying network bundles them all together. You want private channels, you want reliability, you want in order. It's not. You know, it comes all together. You can't say I want one without the other. Okay. So Datagram sockets, no guarantee, built on top of UDP, message size limit. Stream sockets built on top of TCP/IP. And the nice thing here is that you've got the same abstraction to capture both, and you can in fact dynamically go from one to the other without changing your program. At least that's what the Unix sockets allowed, and I think in Java that's also probably possible. Okay? So this late binding that we wanted. So the trouble though is that we've got to make a choice here. If you want to choose, well, I guess with Datagram sockets also you could use stream I/O, so I take that back. But yeah.
What do you mean by in order?
In order, so if I go and send hello first and world later, world will be received after hello.
That's real Datagram socket. That's real.
Of what?
It's not.
Datagram socket.
Not at all.
Yeah, the network, they can get routed. different.
Hello could go through the Pacific side, and the world could go through the Atlantic side and receive the.
But from the time it actually reaches its endpoint, it's reassembled.
No, not in datagrams.
Guarantee in order.
No, there's no sequence numbers in Datagram. Okay, that's the whole point. There's no overhead, it's fast, but guess what? Most probably it will be arriving there. So, you know, I built a demo of an application which was which required reliable connection. But whenever I had to give demos to my funders, I would go just transparently change from TCP/IP to UDP and make it go fast. I knew no packets would get lost, at least in my local area network. So I know this late binding is possible, and I know it's much faster. Okay, and so okay. And because you have this thing that is it stream or not call, you can go one way or the other. And we see that in Java we've got Datagram Socket and Socket, so it's trying to separate these two concepts to some degree. But in the Unix concept, it was all one ID. You got just the same ID back. Okay. So you can either use explicit operation to send and receive. In the case of packets, you saw the sends and receives. Would it be important, supposing you're doing stream-based I/O, we saw that we did not have to do read and writes, sends and receive. We could just do read and write. Can you imagine, even in the TCP case, when sends and receives may be useful? And actually, it's breaking the TCP idea, but there's a notion of an urgent message. Please send this with a higher quality of service than the other messages, in which case you need to sort of have a special call. So in Unix, there was something like that. I don't know about Java. Okay. So I should really say implicit versus explicit. Non-connection based IPC, which is what Datagram is IPC, can use both implicit and explicit addressing. Okay, explicit addressing means that with each packet I go and say where it should go. Implicit means that when I created the handle, I said where it went, and then it's just implicit. Okay? But in the case of connection-based IPC, I won't say TCP/IP. I'll just say where you have private channels. Okay, then you use implicit addressing. Okay, so the title here should be implicit versus explicit. And you can also define access rights when a connection is opened. You know that in files. You can open it for reading, writing. So there's all kinds of access that you can do when you